All right, page 458 is section 6.4. Yesterday we talked about what a vector is and some of the operations that you can do with vectors. We added them, we subtracted them, we did scalar multiples of them. So today we want to do a couple more operations with those vectors, and the first is that we want to multiply those vectors. Now, there are actually a couple of different ways that you can multiply vectors, and so we need a way to differentiate them. When you multiply, you know how sometimes, like if you're saying 2 times 3, sometimes you would just put a dot in between the 2 and the 3 to show multiplication. Sometimes you would put like an X in between 2 and 3 to show multiplication. So because of that, with vectors, we're going to have a dot product and a cross product, so that when we have the two different ways of multiplying vectors, we can differentiate between them. So we're going to look at dot product today. So they tell me that if you want to find the dot product of two vectors that are in component form, that you can multiply the dot product by doing the product of the first value of each vector plus the product of the second value of each vector. So for instance, if I have u is -1, 3, and I have v is 2, -4, and I want to find their dot product, I'm just going to say -1 times 2 and 3 times -4. And then I'll just add those two products. So I'll get -14. So that's how I find dot product. Now, on page 658, they give me some properties of dot product. And I know sometimes these boxes you have a tendency to just kind of brush over, but a lot of times they'll save us a lot of time and energy. And that's the case with the one on 458. The first thing they tell me is that u dot v is the same thing as v dot u. So if you have, it's like 2 times 3 is the same thing as 3 times 2. You can multiply dot product in any order. Second thing it says is that if you have the 0 vector, the dot product of the 0 vector and any other vector is always going to be 0. Third thing they tell me there is basically distributive property works. If you have u dotted with a sum, v plus w, you can distribute that and say u dot v plus u dot w. The fourth one says that if you have a vector dotted with itself, it's just going to be its magnitude squared. And then number 5 says if you have a constant times a dot product, you really can do that in any order. Like you could do the constant times u and then dot it with v, or the constant times v and then dot it with u, or u dot v and then multiply by the constant. So just several different ways that we can change up our dot product. So when we go back to example 2, and these little numbers out here in the margin are the homework problems that correspond to the example. When we go back to example number 2, they asked me to find v dot u and then multiply that by w. Now, if I know that first property right there, that u dot v is the same thing as v dot u, I don't have to do another dot product. I can just say, okay, since v dot u is the same thing as u dot v, I already know that's -14. It wouldn't be wrong if I did the dot product of v and u. I'd get -14 again. I'm just saving myself some time and hassle. All right, so now I'm back to scalar multiplication that we did yesterday. Take that -14 and multiply it times the vector. So I would end up with -14 times 1 and -14 times -2. All right, the third thing they show me there is to do u dot 2v. And according to that last property that we just looked at when you had a constant or a scalar being multiplied by a dot product, we said that you could do the dot product first and then multiply by the scalar. So again, I've already found the dot product of u and v to be -14, so I save myself the work and just say 2 times -14 is -28. Again, if I had done the scalar 2 times the vector v and gotten that component form and then dotted that with u, I would have gotten the same answer, just saving myself some work. Next thing they tell me on the bottom of page 459 is how I can find the angle between two vectors. All right, so let's say that you have two vectors drawn. You're just talking about the angle that is in between those. And we're going to specify that we're looking for an angle between 0 and 180. Because if you're looking at an angle between two vectors, you would have a smaller angle and then you'd also have a larger angle. I think most of us, when we look at this and they say, what's the angle between the two vectors, we automatically think of the smaller one, not the larger one. But just to be clear, they've told us use the angle that's between 0 and 180, so we know which one they're talking about. So here's what they tell me. To find that angle, find the dot product of the two vectors and then divide it by each of their magnitudes multiplied, and cosine will be equal to that value. So let's look at one of those. For our next example, they give me this one in standard unit vector form. So yesterday we were working more comfortably in component form. So let's switch these to component form first. What would 4i plus 4j be in component form? 4, 4, yes. What would negative 2i be? Because it's negative 2i plus what j? 0j, right. So what would its component form be? Negative 2, 0. Perfect. So let's find their dot product for the numerator, and then we'll find their magnitudes for the denominator. Okay? So for the dot product, we're going to do 4 times negative 2 is negative 8, and 4 times 0 is, so that dot product is going to give us negative 8 plus 0, or negative 8. Now we need the magnitudes. So let's start with the magnitude of u. We did magnitude yesterday. Remember, we said that it would be the square root of the first value squared plus the second value squared. So that would just give us the square root of 32. And you can simplify that radical if you want to, or you can leave it as it is. We'll look at that in just a second. All right, then let's find the magnitude of v. V was negative 2, 0. So again, when it's already in that component form, it's just the first value squared plus the second value squared. So we'll just get the square root of 4, which is 2. So according to my formula, I've got cosine is equal to negative 8 over 2 square roots of 32. At this stage, I could throw that whole thing in my calculator, right? Hit the Jeopardy button on my calculator, inverse cosine. No need to simplify that radical at all. Okay? But if I did simplify that radical, this is just 16 times 2. So square root of 16 is 4. That would be 4 square roots of 2 times 2, so 8 square roots of 2. And then the 8, top and bottom, would cancel. So I would be left with negative 1 over the square root of 2. If I rationalize that, I'm going to get negative square root of 2 over 2. So I mentioned that just because that was a value that we knew a little while back, and seeing it in that fashion might help make the answer make a little more sense to you. So I could throw this into my calculator, or this into my calculator, or this into my calculator, and when I do inverse cosine, I'm going to get 135 degrees. If I were doing this from the values that I knew from the first quadrant, I know cosine is equal to square root of 2 over 2 at 45 degrees, and I know cosine is negative in the second and the third quadrant. Remember, I'm only interested in angles between 0 and 180, so I would just give the second quadrant, which would be 135. All right, so then the last thing that they talk to me about is how to tell if vectors are orthogonal or parallel, or neither. All right, what does orthogonal mean? Well, if two vectors have a dot product of 0, then that means that they are orthogonal. And that just means it's very similar to perpendicular. They're meeting at a right angle. Remember we said that if you dot the 0 vector with anything, you'll get 0? So if that's true, and if the dot product is 0, the vectors are orthogonal, that means the 0 vector is going to be orthogonal to every other vector, because when you dotted it with something, you would get 0. And then they tell me that two vectors are parallel if one is a scalar multiple of the other one. So, for instance, if I could say one vector is equal to 2 times the other vector, so like one vector is double the other vector. So, in the last example, they give me a couple of vectors and they ask me to tell, are these vectors parallel, orthogonal, or neither? So, probably the easiest thing to check is orthogonal. Let's start with that. Let's start with dot product. Okay? So, I'm going to need to compare u and v, u and w, and v and w. Those are all the possible combinations for those vectors, right? So I'm going to start with dot product. So let's do dot product of u, v. So dot product of u, v, we're going to do 4 times 3 and get 12. And then 3 times negative 4 and get negative 12. So when I do 12 and negative 12, I get 0, which means, yes, they are orthogonal. When you get a dot product of 0, that means those two vectors are orthogonal. All right, let's try u and w. Same exact scenario. I'm going to do the dot product of u and w. So I'm going to do 4 times 2, which is 8. and I'm going to do 3 times 3 halves, which is 9 halves. That's not 0, so they're not orthogonal. They may be parallel, they may be neither, but they're not orthogonal. All right, find the dot product of VW. Find the dot product of VW. All right, what'd you get? 0, yes. And that means they're orthogonal, right? Okay, so they said, are the vectors orthogonal, parallel, neither? We already know these are orthogonal and these are orthogonal, so that just leaves us with this middle set, u dot v. If it's not orthogonal, I need to check and see, are they parallel? If they're not parallel, then they're neither. Okay, so if they're parallel, that means that one has to be a multiple of the other. So that would mean that if I take vector u, it should be equal to a multiple of vector w. Or you could write it the other way. You could say w is equal to k times u, either one. So vector u was 4, 3, and vector w was 2, 3 halves. You can approach this with common sense, or you can write a formula for it. Let's start common sense, and then we'll go to formula. I could look at this and say, okay, I need the first value over here to be equal to the first value over here if they're going to be multiples, right? So I could say what times 2 gives me 4, and that would tell me that k has to be 2, right? And so that's what I would want to check. I would want to see, okay, 2 times 2 gave me 4, but is 2 times 3 halves going to give me 3? Is it genuinely going to be a multiple of one vector that equals the other? If you're more of an algebraic formula person, what you could do is literally write yourself an equation and say, if they're multiples, the first value over here has to be equal to the multiple times the first value over here. So just write that as an equation. 4 has to equal k times 2. So we could say, okay, if 4 has to equal k times 2, divide both sides by 2, and k has to be 2. So in either case, we've got this value, so now let's check and see. If I go through and do that scalar multiple, 2 times 2 is 4, and 2 times 3 halves is 3. So yeah, one is a multiple of the other, so yes, they are parallel. If I checked and the dot product wasn't 0, and one was not a multiple of the other, then I would just say neither. Okay? All right, so here is our homework for tonight on section 6.4.